my name is Eyberg. I'm one of the founders over at Nano VMs, and this talk is about creating open source Unikernel packages. If you want to follow along, these tools, ops and nanos, are open source. You can download it, play along. If you don't like this way of installing via curl, there's binary downloads, and you can also build from source. Anyways, let's just kind of jump into it. For those of you that aren't aware of the term Unikernel, essentially it's a way of deploying your software as a single isolated virtual machine. It only runs one application and actually has no capability of running multiple applications in the same VM. So it's very different from Linux in that regard. As to why you would want to, one reason is performance. Many Unikernels, Nanos included, which is the one we're going to be showing you, can run many different applications, twice as fast on Google, 3 times as fast on Amazon. So these are Nginx, Redis, Go web servers, Rust web servers, all that good stuff. And there's no like algorithmic magic going on. It's simply because of the architecture at play. If you go to Amazon, you spin up an EC2 instance that has one thread. Even though that Ubuntu or Debian instance has 100 different processes all fighting over that one thread. Whereas in a Unikernel, it's only that one process. And that's not to say that we don't support multiple threads. So you can use as many threads as you have hardware capable. So that's one reason. But there's many other security and complexity as well. The next kind of question that people have is, how is this different from Docker and Kubernetes? It's a world that a lot of infrastructure people might be used to. There's quite a few differences, actually. It's not simply containers 2.0, which a lot of people seem to think it is. It's actually very, very different. So in Docker land, keep in mind that Docker's reusing existing Linux subcomponents, right? So Docker still has concept of a shell. A shell doesn't even make sense in Unikernel land because it implies that you're going to run more than one program. I type in ls or cd or something like that, and we call those commands, but what are they at the end of the day? They're other programs that we're running. Shells don't even make sense in Unikernels. Docker, again, runs on top of Linux, whereas Unikernels, the vast majority of them don't have Linux in them. There are a few projects that kind of have touched it. In Docker and Kubernetes, we have the concept of users still. There are no concept of users in Unikernel land because, again, there's this lack of user land available. In Docker land using Linux clocks in about 30 million lines of code. Half of that is all drivers. So, think a driver for each and every network adapter, a driver for each and every storage device. There's a lot going on there. And the reason is because, Linux was made to run on actual real computers, right? Whereas Unikernels only really run on virtual machines. And so there's a lot less stuff that they have to deal with. In Docker land, we support many processes. That's not the case in Unikernels. It's single process by definition. And although it can run multiple threads, if you're using Docker, you're probably using something like Kubernetes or something. You're going to take a performance penalty by doing this simply because a lot of the layers are duplicated. So think overlay, underlay networks. Same thing with the storage layers. On Unikernels, what we do is we actually deploy these as VMs to the cloud. So they're not only just running faster than a Docker container, but they're actually running faster than Linux in many, many cases. Also, when it comes to security, Kubernetes kind of breaks well-known security boundaries. If you take a classic, Debian server on Amazon, if I pop a shell on that box, I have access to that box, but I don't immediately have access to every other VM in your infrastructure. That's not really the case with Kubernetes. I mean, if I break into one of your pods, your entire infrastructure is probably hosed. And so Unikernels kind of take a very proactive stance towards security issues. We have many of the same security primitives that you'll find in Linux, like ASLR and page permissions and all that sort of stuff. But there's things like there's no shell, there's no users, you can't fork a new process. It's kind of locked down from that point of view. And then the very last thing is complexity. If you go search for Kubernetes on Google, complexity is a very common word that comes up with it. Unikernels are actually much more simpler to use, namely because it removes a lot of the ops complexity that exists. So you can't just like all the network configuration, all the volume configuration, the orchestration, we push all of that onto the public cloud of your choice. And so you don't really have to deal with any of that. All right, so that's kind of the quick run through. Let's get into the actual parts of the talk. Let's say we want to run a simple hello go world as a unikernel. So this is a very common example. You'll see in all of our examples, it's, I don't know, 10 lines of Go code. And so we take that and, using ops, we can do ops run port 8080, our web server, and boom, it's running. So in this ops run, it builds and runs the unikernel kind of on demand. So Go is pretty simple, and as you might be able to tell, this is being done on a Mac. This is relatively simple because in this case, the Go binary was statically linked. There's really not much there. In fact, we can take a look at the file system using this dump command. So dump, just like the dump and makefs commands that you might find on Linux, we've created a version of here. We throw it in the tree output, and you'll see the entirety of this file system. So we have the certs, obviously, if you want to do anything. TLS, you want those. You'll notice you see this etc password file too. And you might be wondering, why is that there? Because I thought unikernels don't have users. And if you actually look at the file, it's just a stub. And the reason why is because most applications, maybe not in this case with Go, but many are going to be linked with libc, which is the dominant glibc, the dominant libc alternative out there. And so if you look at some of these functions, they're going to expect to see something, even if it's a stub, even if it's completely meaningless. And so there's many cases where we've stubbed out expectations for conformance to certain standards. But looking towards the future, it's not something that you would expect to have. That's your resolve conf. Obviously, if you want to change your IP addresses into actual domains. And then you can also see proc, and you might be wondering, well, that's a Linux specific thing, isn't it? And again, in this case, the Go runtime does expect to have a few things, like proc self-exe, for instance. It's a pseudo file just the way it is in proc. You'll note that if you actually look through the nano source, our proc is nowhere even close to what you would find on Linux, though. There's probably 4 or 5 special files that we actually support, and we don't always include all of them. And then, libnss is here. The G is the actual executable. So very, very small file system. And part of that is just because it's Go. All right, so let's move on to Node.js. This is a little bit more complex, but it's the exact same example. We have that web server listing on 8083, but this time we're using a package, which is part of this talk, right? So so in this sample, we're doing ops package load. We point it at this node runtime port 8083. The -f is for force build. -n says use the nightly branch. So every night there's a branch of Nanos master that's cut, and you can use that. And then -a is just like a pin the arguments. So in this example, we weren't able to just load the binary as we were with Go, because Node is an interpreted language. And so this time we're actually taking the contents of the Node package and combining it with this hi.js to create our unikernel. And so the actual elf binary that we're executing is the Node executable, right? So let's look at this file system. This one's a little bit bigger, and you can kind of see in these libx8664 links GNU, you can see all the shared libraries that this particular Node interpreter was linked to. You'll see things like the package manifest and even this proc mem info. So proc mem info is something that Node does definitely want to see. But if you look at that, again, this is one of these little stubs that we just kind of hack away at. This is a particularly smaller example, and we can kind of look at the tree view here too. after the image is actually built. Contrast and compare that to something like Python, though. So in this example, the Python 3.8.6 package has 9,000 some odd, 9,500 files. So it's not small, right? You know, some people think that unikernels are automatically going to imply smaller packages. That's not always the case. I mean, if you're dealing with something like a JVM or something, particularly with a Python machine learning frameworks that you'll find, these images can actually get, you know, fairly large. Again, we're not doing any magic here. If your application needs one of these files, then it's still going to need it. So that's where a lot of these packages come into play. All right, so let's jump into how do you actually create your own package. That's part of this name of the talk. In this case, this is just showing how this Lua package was made. And so if we look at it, it's a tarball at the end of the day, very similar to other packaging concepts out there. And if we look at the inside of the tarball, we have the program. So in this case, it's the Lua interpreter. We have package.manifest, which we'll take a look at, but it's just a JSON file with configuration information. And then we have the sysroot folder. And so everything inside the sysroot becomes your root file system. Whatever you put into there will show up in the root file system of your unikernel. So, you know, again, here's your shared libraries. Your package manifest, by convention, this is what we kind of expect in it. It's not necessarily mandatory, and I could see this dramatically changing in the future. But you know, we have the path for the program name, so Lua, and then any arguments that it might expect, and then the actual version. The semantic version, again, here it's by convention, but definitely not mandatory. And so that, you know, again, that might change in the future. There's lots of applications that don't use this versioning system. That's totally fine. But that's just an example. If you're wondering how you might find out which libraries that you need to include in the package, LTD comes into play here. And so, you know, you just run it on the binary of choice, and you can grab pretty much most of what you would need. Now, this isn't true in all cases. There's definitely certain libraries that might be opened at runtime. And so in that case, there's other techniques to figure that out. But as a package maintainer and as a package creator, those are techniques that we would expect package maintainers to know, but not necessarily end users. So as an end user, I wouldn't fret about this at all. This is totally a package maintainer type of deal. You know, DNS, for instance, is one case where you're not going to see this in LDB output, but you definitely will still want it. And that's just because of the way Linux actually runs these elves. There's a few more that you'll use. So in this case, we have like libnss, libresolve, things like that. There are other ways of doing this. I showed you the manual process, but this is a process that one of our end users hacked up. And basically, he got tired of building, I guess, node packages by himself. And so basically, he did this ops package from Docker. And so if you have the Docker daemon running, you can just download this image and import it immediately. And so, again, this is running on a Mac, but you know, Linux works as well. So you can import it, and then you can run ops package load with your newly created package. So it's a pretty fast and easy way of taking any Docker image and turning it into a unikernel. These two commands take like, I don't know, 2 minutes on my connection. A third way. So this is another interesting thing that one of our end users brought up. Basically, we have the capability of setting up build envs for some of these packages. So one use case that we'll show you is the use case where, say you're on a Mac, but you have a Linux dependency. So how do you do that? Well, normally people will be using Vagrant, or they'd be using Docker, and Docker on Mac is using a Linux VM. And so, so you have access to that. But if you don't want to use that, we made this little ops env install. And so this will use a small little Linux VM to run a series of commands and create your image for you. To give you an example, there's this Redis fast driver that's used for Node. And so this uses a native library that's very easy to build on Linux, but it's not so easy to build on Mac because we're dealing with different file formats. And so what you can do is you can pass it this build.txt, give it the commands that you want, and it will execute that in the build env. And then you can toss it this config.json, which is basically the same thing as you would normally use if you were building your own Node package. So in this case, we tell it, hey, we're expecting some Node modules to be installed, in particular the Redis package. And then we can run this command ops and build.txt-c, pass it config.json, -r for recursive. And then what we're saying, if we run this on, say, a Mac, is we want all the artifacts to plop into the host directory with that trailing period there. And so this is executing inside of a guest, but then it's going to take the output and throw it on the host. And as you can see, this is what gets copied over. So we have, the libraries, we have the Node modules, we have all the stuff that we need to actually build that in package. And then you can kind of see the tree view of this. And then our config.json basically becomes this, where we can specify the directories we want, files we want, the program, and the args. And finally, we actually execute this. So now this is running on your Mac, not inside of a Linux VM. It's running on your Mac as a Unikernel using the node that you built inside the Linux VM, but it's just running there natively. And so this is like super fast because, again, we're just booting into the Unikernel. There's no Linux being booted into here. This boots up instantly. So, and you can take that and then you can deploy it to Google or Amazon or anything like that. That was a very quick run through of the stuff. Happy to kind of take any questions that might exist.
Thanks, Ian. We have, let's see, there are no questions in the room on Element yet. I'm curious. Is it easy to build a Unikernel given any application? Like if I had my own Python application, would I be able to build a Unikernel for that?
Yeah. So with with the Python example that I showed, that Python 3.8.6, what we do is we create packages for many of the different packages that you might use, like apt-get with normally. So we don't expect end users to be creating their packages. We expect package maintainers to be creating those packages. And so as an end user, you might just use like any of the numerous packages that are already exist. I think there's 70 or 80 different packages available in the ops toolchain right now. But if you want to create your own, these are some of the processes that you would go about doing so. And then there's, as I showed earlier, there's many different programs that don't necessarily need a package either. So, if it's something as simple as like a Go web server, you don't really need to create a package. You can just create that Unikernel on demand. I do see this other question from Park. When you run a Unikernel on a Mac, what VM is it running in? So good question. The Unikernel, at the end of the day, it is a VM, but there's no Linux running there. When you boot it up, it's literally just that image of whatever you threw onto the file system, along with Nanos. And so Nanos is something that we might have glossed over earlier on, but there's this popular misconception that Unikernels aren't operating systems or they don't have kernels. Every single Unikernel out there has a kernel, every single one of them. And so it's they're going to use that kernel implementation. Now it can be super easy and simple, and it can also be dramatically complex as well. But what they all share in common is that they're not a general purpose operating system like Linux or BSD. And just to be clear, Nanos, if you go to like nanos.org, That's not like a Linux distro at all. There's no Linux kernel inside of it. It's the Nanos kernel that's actually running. And then also as a follow-up question, but on the Mac, is it just a Mac process? Can Nanos run as a Mac process? So technically what it's doing is ops forks out to QEMU, and QEMU is the machine monitor that's actually running. So you have that as a process running. And by default, it'll run in user mode, which is mostly emulation. But if you have HVF enabled, which most people would have, it's going to use hardware acceleration, and so then it's going to run like super fast and performant. So yes and no. Yes, it's running as a Mac process, but it's orchestrating QEMU around it. And so if you deploy to something like Google, for instance, Google is built on KVM, and you know, all your VMs are running on KVM there. On AWS, all their older instances run Zen. Their newer Nitro-based instances are a variant of KVM. We support all the different clouds. They all have their own. They all have their own hypervisor that they're using, and so we have support for all the major clouds. But yeah. And by the way, you don't have to use QEMU on Mac either. There's VirtualBox support and all the other hypervisors as well. That's just the default. So
we have time for a couple more questions. I think there's one on the chat. How do you handle networking for multi-container apps?
Yeah, good question. So it kind of differs, but basically, if you were deploying to, say, Google, where nanos.org runs as a unikernel, ops.city runs as a unikernel there, Google will basically assign your VM a tap device. This, by the way, all taken care of for you. This is one of the beautiful parts of unikernels, in my opinion. So Google actually handles all that networking for you. You don't have to touch any of it. It boots up as a VM. It gets its IP address, whether it's private IP or public IP or IPv6 versus IPv4, and then you just talk over the network. So that's one defining characteristic for unikernels is if you rewind back to like the mid 90s, we had a lot of software that might exist on Mars, the database server, or Jupiter, the web server, or whatever, and so they would use IPC to talk back and forth between one process and another. But the reality is that since we all have these massive tech companies now, most of our software doesn't even fit on one server anymore. You know, if you're an engineer at a high growth tech company, you don't have one web server, you have like thousands of web servers. You don't have one database server, you have thousands of database servers. None of our software fits on a single server anymore. And so that's where unikernels kind of come in, and they're saying, hey, we totally outgrew the operating system a long time ago, and we just didn't even realize it. So yeah, everything talks across the network.